let's review and talk about cell potential real quick. Cell potential is that driving force, it represents the driving force of going the electrons in one direction. It's the voltage, how much electron flow can be, generated by a galvanic cell. We're looking here at the beginning of these notes talking about galvanic cells, voltaic cells, which are the ones that are going to be thermodynamically favored on their own. They can run on their own and so forth. We'll be talking about electrolytic cells at the end. Those ones, of course, are thermodynamically unfavorable, and we'll talk about their characteristics later on. But the total cell potential is the sum of the cell potential at each electrode. In general, that's a general statement. The sum of the potentials at each electrode. And we're looking at the reduction potentials because remember those were all created from the hydrogen, the standard hydrogen electrode, and those were generated at 25 degrees Celsius, 1 molar solutions or 1 atmosphere gases, depending on what you're talking about. They were all at standard conditions and so forth. But the basic way of doing the equation to find the cell potential, E cell, is going to be the potential of the oxidation plus the potential of the reduction. So I flip my reduction potential and change it to oxidation for that part of the reaction, and then I just add them together. And if it becomes a positive E cell or positive cell potential, I know it's thermodynamically favored and it's a galvanic cell. Now, if you're looking at the reaction up here, you'll see zinc is being oxidized. So that's going to be this part, the oxidation E cell part, and the copper is being reduced up here. So that's going to be this part, the reduction part of calculating the E cell. Now, most of the time you would look them up on the tables in order to find them, especially if you're doing a problem set, because the book makes you look them up at the tables. However, for your free responses, you won't ever have to look them up because they will be in the question themselves. So you will be provided the standard reduction potentials needed for that particular question. Now remember, standard reduction potentials, half reactions being oxidized, will need to be reversed. That's the one thing you do, you reverse them and then you change the sign. Also remember standard reduction potentials or oxidation potentials, if you multiply through by a factor, that does not change the potential value. Only reversing it do you change the sign. You never multiply through by a factor. This is an intensive property. There's only a certain amount of electrons that are going to flow over at any given time. So there is no multiplying factor for these at all. All right, let's look at this example here. We're going to write a balanced cell reaction and calculate our standard E cell for this particular one. Now they gave us both the reduction potentials, and I'm creating a galvanic cell to run here on its own, thermodynamically favored. Which one am I going to flip? So I can guarantee that I'm getting a positive cell potential or E cell. Which one has to be the oxidation one out of the two in order for it to be a galvanic cell? I have the gold being reduced to form the gold solid, and that's a reduction potential of 1.5 volts. And then I have the bromine, if that's being reduced to bromide, I get 1.09 volts. So which one do I flip here to make sure I still get a positive E cell when I add them together? Anyone? Anybody there? Okay. Well, looking here at my two possibilities, in order to guarantee a positive overall cell potential, I need to flip the bottom one. So if I flip this one, I get bromide. Actually, there should be a 2 here, so put that there. Going to bromine plus the 2 electrons. This is going to make this an E-ox, which is going to be negative 1.09 volts. So we're going to ignore this one, because remember this is redox, so you need an oxidation and a reduction. So here we have our oxidation, 1, and we have our reduction. Now we can add them together. We add them together, we get 0.41 volts, like so. That's going to be the E cell for this particular one, and it makes it positive. If I flipped the top one, though, it would have come out to be a negative E cell, so that's not the one I want to choose to make the oxidation reaction. Now we have to combine these two to do the balanced, and we balance them based off of the electrons. We have 2 here and 3 here. So now I do need to multiply through and get a least common multiple so that I can balance them by the reaction. So I'm going to multiply this top one by a 2. I'm going to multiply this one by a 3. When I do so, I end up with 2Au3 plus 6 electrons, giving me 2 Aus. And I multiply the other one, which is going to give me 3 times 2, so that's 6 bromides, going to 3 bromine liquids. Although they didn't, did they put the phase up there? Oh, they said it's a gas, sorry, gas. And then we're going to get 6 electrons out of it as well, because 3 times the 2 here. Now we can combine them because this is going to cancel. So technically we have an exchange of 6 electrons going on here. So this is like 6 moles of electrons that are being transferred between the oxidation reduction reaction. Then all you would do is combine them. So we get our 2Au3 plus, this is aqueous because it's an ion, plus our 6 of the bromide, which is aqueous. That's going to give us 2 of our gold solids and 3 of our bromine gases. So this would be the overall balanced reaction. Remember, redox is always balanced based off of the electrons, not of the individual elements. And actually, this reaction is showing a transfer of 6 moles of electrons. All right, we have 6 moles working this reaction. So there we have it. All right, description of the galvanic cell. The reaction always runs spontaneously in a direction that produces a positive cell potential. So when we say positive cell potential, we're talking about the E cell here. That's what we're referring to, positive cell potential. And when we say spontaneously, the better term probably would be thermodynamically favored. That's what we want to say as well, that for a galvanic cell, it needs to be thermodynamically favored and have a positive E cell. So that's the basic description of the galvanic cell. Has to be thermodynamically favored. You set it up so the anode and the cathode, that's going to give you, when you look at their reduction potentials, you flip the one, get the oxidation potential, add it together, make sure it ends up being a positive E cell to set up the galvanic cell. Then you know the electrons will flow in one direction and it will happen on its own. It won't need any outside intervention in order to make the reaction occur. That's what we're talking about when we say thermodynamically favored. Couple other things, description, 3 things for a complete description. Cell potential has to be positive for a galvanic cell, kind of define that. And you have to have a balanced overall cell reaction, and this is going to be based off of the electrons, right? You balance it off of the electrons. Second part here, direction of the electron flow, don't forget. Direction of the is going to be anode to cathode, always. That's how the electrons flow from the anode to the cathode. So you set it up that way, and designation of the anode and cathode. We designate them, of course, based off of this is going to be the oxidation reaction, and the cathode is going to be the reduction reaction. So when you're designing or even looking at a problem, because there's kind of one of 2 ways they can give this to you. They can give you the reaction. They can give it to you unbalanced or balanced, but you have to figure out what's being oxidized or reduced. So you know what's the anode, what's the cathode. Or they could give you a picture of the cell and you have to look at it and decide what's going to be the anode or the cathode based off of what components are in there and your balance reaction and so forth. Don't forget too that there's an easy way to remember this. We do anox for anode, cathode is red cat. So reduction takes place at the cathode, the oxidation takes place at the anode. Very easy ways to remember that. All right, free energy and cell potential. New equation, this one is located on the formula sheet, which on one of the review sessions I plan to go through the formula sheet and make sure everybody knows where everything is. It will be in the front of the test. There is a copy of it posted on Classroom, but you can also look at it on AP College Board site. They have it there. You could pull up the admin 1 free responses. It's located in there as well to get yourself a copy of the formula sheet if you haven't already printed one out. Now, formula sheet, delta G equals negative NF cell potential, E cell, and is of course the number of moles of electrons. So as we were talking about in that first exercise, it was a transfer of 6 moles of electrons. So that's where you're going to be determining it, how many electrons are being transferred. That's what the N value is, how many moles of electrons are being dealt with here. Faraday's constant is 96,485. Don't worry, that one's on the formula sheet. You do not have to memorize it. And its use as a conversion factor, you'll see later, we've got the coulombs over the 1 mole of electrons, so it's easily set up into dimensional analysis using a fraction, and we will be using it as a conversion factor. Now the last part, the E cell, is going to be measured in volts. So this is really their E. That's going to be measured in volts, but a volt is actually a joule, 1 joule per 1 coulomb, like that, 1 joule per 1 coulomb. Now that's why am I showing this? Because this is how this equation works in order to cancel out the units. You've got your moles of electrons, so N is going to be the moles of electrons. Right here, moles of electrons. Faraday's constant, this one is going to be coulombs over moles, 1 mole of electrons. And then the volts over here really is joules per coulombs. So if you look here, how do we get delta G from that, the unit? Well, the coulombs cancel, the moles of electrons cancel, and now we're left with joules for delta G. You would get the joule here, and then you would change it over to kilojoules, because we usually report delta G in kilojoules, divide this by 1,000, and get your delta G in kilojoules. That's kind of how the units cancel for this particular equation. And this one takes the free energy, and that's the delta G, and it now encompasses it with the cell potential, which is the E, with the little degree symbol, which is at standard conditions. So how do the units cancel? Well, I already did that part, but there we go. All right. One thing to remember too of how the relationship is between delta G and the cell potential. E cell is less than 0 or negative. Okay, negative E cell means that delta G is positive. Okay, and this is thermodynamically unfavored. Sometimes, and in general, you could say like per mole of reaction, because that works usually. But they should accept kilojoules or kilojoules per mole of reaction for the unit for delta G. Good question. And here the delta, or the cell potential, if it is positive, greater than 0, then delta G is negative, and this is going to be thermodynamically favored or spontaneous. So don't forget the relationship between cell potential for electro and Gibbs free energy there. Now, going to go over the Nernst and non-standard conditions. As stated before, standard conditions are, 1 atmosphere for gases, 1 molar solution for, AQ, and 25 degrees Celsius. Those are standard conditions. So what we can do here is use the non-standard delta G equation to derive the Nernst equation. But as you can see here, it eventually ends up canceling down to the E cell equal, or the non-standard E cell, this is what I refer to as the non-standard E cell, is equal to the standard E cell minus RT over NF ln Q. So all of that rearranges, okay, and you end up with this way of expressing the Nernst equation. Now the Nernst equation you can actually calculate and get the numerical values, but a lot of times they don't really want you to calculate. They want you to qualitatively understand the non-standard conditions and how that drives the reaction. This is on the formula sheet. You do not have to memorize it. It's there for you to use. So R, don't forget, is also on the formula sheet. It's 8.314 joules per mole times K. That one's on the formula sheet. Remember, temperature is always going to be in Kelvin, like so. Faraday's constant you just learned. That's the, 96,485 coulombs per mole of electrons. And N here, once again, is still talking about moles of electrons. So this is the 96,485 coulombs per mole of electrons. Now, ln Q, we're going to calculate Q just like we did before with equilibrium. I'm going to show you in the example how to calculate the Q again using the equilibrium expression. But this is the generalized Nernst equation. You can use it off of the formula sheet. Now, at equilibrium, you can derive a different equation to use for from the Nernst equation. Basically, you put in at equilibrium, the E cell is 0, it's basically a dead battery, and K, of course, equals Q. So you can substitute them into the Nernst equation and then rearrange everything. And at equilibrium, the components in the two cell compartments have the same free energy. So that means, that delta G is now 0 as well, and you basically have your dead battery because you have no directional flow of electrons. Now this one is not on the formula sheet, but I'm going to show you how you can easily get it if you need it. You have your delta G equals negative NF E, that one, and we also have delta G equals negative RT ln K. Now because these both have delta G in them, you can set them equal to each other and derive this equation right here. Can get that one. So basically what we get here is we have negative RT ln K is equal to negative NF E here. And all we have to do is divide both sides by the NF, negative NF. This cancels and these become positive. So as you can see, E equals RT over NF ln K. So you can easily derive it from those other two. Both of these ones are on the formula sheet, so you don't have to memorize those. But this is a equation that might go a little bit quicker for you than having to work both of the other two. Now this also shows the relationship between the three equations. Here's delta G, and here's K, because I know they're hard to see. So we have the delta G equals negative NF E, and delta G equals negative RT ln K. Once again, these ones are both on the formula sheet. Delta G equals NF E, that goes between E cell and delta G. This one goes between K and delta G. And then the one we just derived, this one's not on the formula sheet, that one goes between E cell and K. And you might want to utilize it so you can easily figure that out or memorize it if you so want to. Like for example, for this particular problem, let's take a look here. Consider the galvanic cell based on the following half reactions. So this is a galvanic cell. It tells me that. I know in that respect the E cell needs to be positive. It needs to be thermodynamically favored. So when I look at my two reactions here, which they kindly already are going to be balanced because we have 2 electrons already in there, so it's already ready to go. All we have to do is flip one of them to get a positive cell. Calculating this E cell here. Out of the 2, which one needs to be the oxidation reaction? Is it the zinc or the iron? Which one of those needs to be oxidized here to make this come out to having a positive E cell? The first reaction or the second reaction? Yes, we want to flip the first one. So that's what I'm going to do here is I'm going to flip the first one. So this is going to become, here I'm going to erase this above here. So I can flip it above that. So this is going to be Zn going to Zn2 plus the 2 electrons. Now this becomes E-ox and it's positive, like so. And so we don't need this one anymore because we flipped it. Now all we need to do is, cancel down the electrons and we can write out our balanced reaction. So we have zinc solid plus the iron 2 ion in solution, giving us the zinc ion in solution and the iron solid. So that's my balanced reaction there. And then to figure out E cell, I just do 0.76 plus the negative 0.44. Go ahead, mental math that. That's very easy. This is going to be 0.32 volts to equal the E cell. And it does come out positive, so we know it's thermodynamically favored. We're good to go. Now calculating delta G and K for this. All right, so we know the first way we have to go here is the only piece of information we know that can get to delta G is this E cell or the voltage. Which equation do I want to use in order to find delta G? Which is the one that relates delta G to our cell potential? Anybody remember? We just went over it. It's going to be delta G equals the negative NF E cell. This is the one we want to use here. So we're going to go ahead, plug everything in. How many moles of electrons are being transferred for this reaction? What's our N value? How many moles of electrons? Anyone? Moles of electrons? It's going to be, yes, up here are the moles of electrons being transferred in our reaction between the zinc and the iron. How many moles? What's our N value here? Well, for those not sure, it's going to be 2 moles of electrons because we're transferring 2 between our redox. So this is 2 moles of electrons. Faraday's constant, 96, 485. That's going to be coulombs per mole of electrons. And then our E cell, which we just calculated right here, is 0.32 volts, which is joules per coulomb. So this is how we get our units to cancel. Like so, moles of electrons, and then we end up with getting our delta G. Now, if you're going to round it to 2 sig figs, which it should be based off of our cell potential, you should get 62,000 joules, negative, of course, because we want delta G to be negative. In order for it to be a galvanic cell, it has to be thermodynamically favored. Now, I probably wouldn't leave it like this. I probably would change it over to negative 62 kilojoules, like so. And yes, using this equation, you wouldn't end up with the moles on the bottom because the units cancel as such as shown. Now that we've done that part, we can find K. Now for the K part, I probably would go ahead and use the equation that we just generated, one that was the E cell equals the RT or NF Now you can use the delta G equals negative RT as well, but if you're going to use this one, I would make sure that you use your raw number for delta G instead of the rounded one, because that will throw it off. And since you're finding that from here, that's why using this one, this version, is a better deal for finding L and K. So we get R is 8.314. The temperature, add your 273 to that, so this is going to be 298, not 289, 298. And the moles of electrons are still 2 moles of electrons, and times the Faraday's constant 96 or 85, which is the coulombs per moles of electrons. L and K, that's going to give us the E cell, which is 0.32 volts. Now you can move everything back over so that you get L and K. So here I'm going to go ahead and calculate all that. L and K is going to be equal to 0.32 times 2 times 96,485 divided by 8.314 divided by 298. So I'm getting for L and K this 24.923 whatever, and then this we need to do the, remember, do the e to the x on both sides, do the e to the x so that we can get K by itself. So e to the x here, and this is going to end up giving us a K value. K equals 6.7 times 10 to the 10. Which, if you're looking at your numbers to validate your signs are correct and everything, delta G should be negative for our galvanic cell, thermodynamically favored. E cell should be positive, thermodynamically favored, and K should be greater than 1. Definitely, massively greater than 1, 10 to the 10th there. So that is a much larger deal, and definitely going in the direction from the anode to cathode and creating a current where the flow of the electrons producing power. Very good. All right, now let's talk about non-standard concentrations. This is the qualitative analysis where you don't really have to use the Nernst equation, although I put the Nernst equation up here for you. Remember, this is on the formula sheet. Couple of factors. At standard conditions, Q is going to always equal 1 because all of the solutions are at 1 molar. So it doesn't matter if they're to a certain power or whatever, Q is always going to be 1. Do remember too, if Ln1 equals 0, that means this side of the equation is going to completely drop off, and that's why the non-standard E cell equals standard E cell, like so. When we don't have all 1 molar solutions though, we have different deal going on. Due to greater concentration of reactants relative to products, the reaction is driven to the right, giving a non-standard E cell a little bit greater amount than the standard E cell. So if Q is less than 1, because you have more reactants than you do products, I'm going to show you how to recalculate Q again, because I know that's an equilibrium thing. The opposite is true, so if Q is greater than 1 due to having more products than reactants, due to a higher concentration than 1, the reaction is driven left, giving a non-standard E cell that is less than the standard. And don't forget, at equilibrium, Q and K are equal, which means, what does that mean? That means that the reaction has no tendency to occur in either direction, so there's no flow of electrons. The reactants are depleted, so when the electrons can't flow in one direction due to that fact, and they've all gone down to, you know, a free energy of 0, you basically have yourself a dead battery where you do not have a flow of electrons. So all this stuff up here is important, especially in the next set of practice problems that we're going to do. Taking a look at those practice problems. Like here, practice 1, we have aluminum plus manganese 2 giving us aluminum ion plus manganese solid. Here we're saying that the aluminum ion is 1.5 molar and the manganese is 1 molar. We know we're at non-standard conditions because the aluminum ion is greater than 1 molar. How do you calculate Q again? Well, let's look at, so Q is going to be like the law of mass action for equilibrium. We do the products, so we would do the concentration of the aluminum raised to the 2nd power, because it has a 2 here, over our reactants. Okay, and this one's raised to the 3rd power, so we got Mn2 plus raised to the 3rd power. So this still follows regular equilibrium. Remember, we would not include manganese solid or aluminum solid because they're solids. They don't get included into the expression. But now that we have this set up, we can figure out what Q is. Do we even really need to calculate it though? Let's look. Because if we put 1.5 squared over 1 to the 3rd, you don't even have to punch that in your calculator. You know that Q is going to be what in comparison to 1? Q going to be greater than, less than, or equal to 1 here? Yes, it should be greater than. So because of this 1.5 on the top, dividing it by 1, we're squaring it, it's definitely going to be greater than 1. If Q is greater than 1, and also seeing here we have more product than we do reactant, then that means the reaction's driven left. So our non-standard E cell, this one is now going to be less than the standard E cell, because in a way, you know, it's not allowing as many electrons to flow over, so it's a little bit going backtracking the other way. So to justify with sentence form, this is what you would say. You would say Q is greater than 1, more products relative to reactants, the reaction is driven left, and E cell is less than standard E cell. The non-standard is less than the standard. Like so. So keep that in mind. Now let's look at a different situation where we reverse them. We're now giving the manganese 1.5 molar and we're giving the aluminum 1.0 molar, like so. We get this here and we can quickly calculate Q or even just look at it. It's going to be 1 squared over 1.5 right to the 3rd, correct? So Q is obviously going to be what in this case? Greater than or less than 1? Because we're dividing by that 1.5 cubed. So yeah, it's going to go this way this time. And it makes sense now because now we have more reactants. So it should be driven to the right. And therefore, when we drive it to the right, the non-standard E cell is going to be greater than the standard E cell because we're going to the right there. So it should be a little bit higher value and voltage. And so this is a way of manipulating it using concentrations to create more voltage. So the purpose of this would be to manipulate non-standard conditions and create, you know, batteries that have more voltage than less voltage. So So Q is less than 1, more reactants relative to products. Reaction is driven right. So the non-standard E cell is greater. And this is how they create the batteries that have different voltages, as you can see. They can easily manipulate how much is in there inside the battery chambers. Now, this one's a little deceptive, so think about it first before. We have 1.5 for our aluminum, and we have 1.5 for our manganese. If you just glance at it and not consider the overall reaction here, what you think about here is that it's definitely not going to come out what you would think if you don't look at the math, because it's going to be the 1.5 squared over the 1.5 to the third. So Q, what happens to Q here? Is Q going to be greater than or less than 1? Yeah, this one's less than 1 still. So keep in mind, it's going to slightly go to the right and create a little bit larger non-standard E cell than the standard E cell. So that was a little deceptive too, because you're using the same molarities there, but they are different mole relationship in the balanced reaction and will create a little bit driven to the right. This last one you would have to calculate and take a look at it. We do Q, we have our aluminum, so 1.50 squared over the 1.31 to the third. What do we get for our Q value when we calculate this? 1.5 squared divided by 1.31 to the third. So what do we get for Q here? Q actually equals 1.00 whatever. So Q equals 1 here. That means that your non-standard E cell is equal to the standard E cell. So I don't know why anybody would do this. Why not stick with 1 molar solutions? Seems like that would be better just to go with standard conditions. All right, let's talk about electrolysis. This is fun, electrolysis. This is where it's thermodynamically unfavorable. All right, electrolytic cells. Running a galvanic cell backwards by running an electric current through the cell to produce a chemical change for which the cell potential is negative. The cell potential happens to be negative. The power source used must supply a voltage that is larger than the negative E cell for the electrolytic cell, or the negative cell potential of the electrolytic cell. Since we're running it backwards, we're always going to have negative for our cell potentials. So for example, to put it in words, and this was apparently asked on Admin 1, just so you know. Example, if you have the electrolytic cell that has a cell potential of negative 2.5 volts, then the battery that you attach to supply to get it going has to be more than 2.5 volts. It has to be able to overcome the negative potential to make the electrolytic cell work. Keep that in mind. You're also going to see it in the diagram in just a second. So here's our galvanic cell. This is 1.10 volts here. This is your voltmeter. It's measuring. It's going anode to cathode this direction. It is spontaneous. It is thermodynamically favored going on its own. And we have standard conditions because we have 1 molar solutions. Great. Wonderful. Galvanic cell. Now let's compare what would happen if we made it an electrolytic cell. Basically what you're going to see is the chambers switch places. All right. The copper side is now the anode or the oxidation side. The zinc side becomes the cathode. So you're running it backwards. Also, you notice that the battery was attached and with a voltage that was greater than the 1.1. Okay, it needs to overcome, because here if the galvanic cell was 1.1 volts going in the positive direction, your E cell for this electrolytic would be negative 1.1 volts. So your battery has to be greater than that in order to make it run. Still going to follow the flowing from the anode to the cathode, but now it's going this direction instead. It's going the other way, because this now is the anode. This side now becomes the cathode. So once again, pay attention to the fact that if they comment on, they give you a battery that is not power voltage enough to overcome the negative E cell value of the electrolytic cell, it's not going to run. So make sure that you have that down and commenting on it. What is the purpose of electrolysis? Why do we even bother? We got to power it. We got to run it backwards. It's used for electroplating. Electroplating is important for a couple of reasons. Besides improving the beauty of lots of our stuff like jewelry and spoons, and you plate lots of different things with pretty metals that are shiny that we use like for our hardware of our cabinets and lamps and other things like that. But the electroplating also can put a layer of a metal on there that helps be resistant to corrosion. And we don't have time to go into a whole bunch of corrosion stuff, because that's all a redox deal, is the corrosion stuff. However, what happens here, like regular rusting iron 3 oxide, that produces the red rust of the iron components. Anything that's a metal that reacts with oxygen and air, and sometimes it's sped up by salt or sped up by water, any metal can corrode, and it forms a metal oxide on top of it that's the rust. And for iron, it's red, but if you remember, if any of you looked at the Statue of Liberty, and you know that the Statue of Liberty is made of copper, that the rust of the copper actually looks green. That's the corrosion of the copper. It puts that green film on top, which would be the metal oxide for the copper that is being corroded. So there's the two purposes. You have putting the thin layer on top for beauty or some kind of aesthetic value. Do it a lot in jewelry where they plate it rather than make it solid, because the plated ones are a lot cheaper. Same thing with spoons. A lot of the, everybody say my silver. Back in the day when you got married and stuff, you would get full out silver silverware. But really, most people don't do that anymore. They might get plated because it's a lot cheaper, obviously. All right. Now, ways to do electrolysis. Two different ways to do it. You can use a molten, or you can use it being dissolved in water. So, what you can do, molten means you take the ionic compound and you have to melt it down. So it's super, super hot, and that's why we call it the molten state. Remember, ionic compounds have really strong Coulombic attractions in their ionic bond, full charge, high lattice energies. So to melt them down takes a lot of energy, but super, super hot. Dissolving it in water doesn't have to be that hot. You can get the ions in there and be able to do the plating if you want to. Once again, looking at the diagram, you have your voltage source over here. In this case, this is the molten NaCl in here, and it's being run backwards, so we plate, and we're going to get some sodium being deposited onto the electrode. You're also producing chlorine gas as a byproduct too. That's why they're showing these gas bubbles in here. So attaching to the voltage short has this run backward or run that direction. This is how they could isolate and get some sodium metal by itself.